Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020. The title of this lecture is The Heat Equation and Fourier. Beginning with a little bit of math history, Joseph Fourier was a French fellow and he lived during this time period. He studied the mathematical theory of heat conduction and in so doing established the partial differential equation that governs heat diffusion, and he solved it by using infinite series of trigonometric functions. Turns out this is a study all unto itself, and that is called Fourier series or Fourier analysis, with applications being way beyond heat conduction. So we'll back off for a moment, and when people study mathematical physics, they study fundamentally three equations at the outset. They study the heat equation, which is shown here, and so this is in one dimension of the form, k a constant. This is the second partial of u with respect to x is equal to the first partial of u with respect to t, and k is bigger than 0, and so we're going to derive that and talk more about that. There's also the wave equation, and there's a two-dimensional Laplace equation, which is a solution in the two-dimensional plane for having heat conduction if you have 0 temperature on the boundary of the disk that you're studying. So back to talking about the heat equation then. Okay, so we're going to derive this in much the way that Joseph Fourier thought about it. So suppose you have a thin circular rod of length L and it has cross-section area A and coincides with the x-axis on the interval 0 to L. Now if you think about it, that's exactly the picture that we have here. So this is the x-axis. There's a little slice of it going from x to x plus delta x. We go from 0 to L. And the cross section of this, now that's just the circle, has area A. And then we have some additional assumptions. The flow of heat takes place only in the x direction. There are generalizations of this, but we're going to keep it simple for now. The lateral or curved surface of the rod is insulated. No heat escapes from this surface. So we're saying that the only way heat can go is this way. It's not leaking out other places. No heat is being generated within the rod, and the rod is homogeneous. That is, its mass per unit volume, rho, and we're using this for the density, that's mass per unit volume, rho, is a constant. So it's a constant density rod. And the specific heat, you studied this in your physics, we're calling that gamma, and the thermal conductivity K of the material in the rod are constant. So this is made of a uniform metal, for example. To derive the partial differential equation satisfied by the temperature U of x at T, and you see it is a function of two variables because it changes over time, we need two empirical laws from heat conduction. So the quantity of heat, Q, which is energy, in an element of mass M is the specific heat times the mass times U at that point. That's an element of mass. And U is the temperature of the element. And number 2, the rate of heat flow. And when it's saying rate, this is the derivative of Q with respect to T. Or you could think about that being the partial of Q with respect to T through the cross-section indicated in the previous figure is proportional to the area of the cross-section and the partial derivative with respect to x of the temperature. So QT, that's the derivative of Q with respect to T, is minus Ka, and this is the partial of U with respect to x. And since heat flows in the direction of decreasing temperature, it tends to make colder places warm. The minus sign is to ensure that QT is positive when UX is less than 0. The heat flows to the right, and negative for UX greater than 0, the heat flows to the left. And since this rod, little sliver that we're talking about, is very thin, X and X plus delta X, we are taking that UXT is the approximate temperature at each point in that interval. And nature is continuous, so that's not a bad assumption. Now, the mass of the slice is m equals rho, which is the density times the volume. That's the volume, cross-section times the depth of the cylinder. So what we can do is we can substitute in for mass this, and we get this expression, and we're calling this 6. We'll refer to that later. Moreover, or furthermore, when heat flows in the positive X direction, the heat builds up in the slice at rate of, and we're just taking the difference between the two, and we're doing algebra to get this expression. Now notice that this is starting to look like a difference quotient, but this is UX, so that's already a first derivative, but this is X plus delta X minus X, so you see that's setting up to be a derivative when we take a limit, and that's going to end up being the second derivative in a bit. But now, first we're going to differentiate 6, this equation here, with respect to t, and everything is a constant except u and q, and so those are where the derivatives go. So now we're going to equate 7 and 8, and we get this expression when we solve for ut. And now what we can do is we're going to say ut doesn't depend on x, so I can take the limit as delta x goes to 0 of this left-hand side. And when I do that, I get this constant u double x, that's u, the second partial with respect to x, is equal to ut. And it's customary to let k is equal to small k equal capital K over those constants, and that's the thermal diffusivity. And now we have generated the heat equation. But now what we're going to do is we're going to consider not only the heat equation but boundary conditions. So we're going to insist that we're kept at 0 on this side and 0 on this side. That's what we get there. And we're going to say that when time equals 0 across here, we have an initial distribution called f of x. And so that's what we're going to be solving here. So this is the boundary value problem that we're going to solve, is this. And this is going to be continued in lecture 41.1.